Okay, let's talk about lipids, the greasy hydrophobic molecules. So we're going to move on to lipids, and lipid is kind of, we tend to think of lipid as greasy, oily stuff is not soluble in water, right? So just think of your salad dressing, how that's not really soluble in water. And we tend to think of these different food components as lipids right here. So here we have like cheese, ice cream, lard, butter, oil. These are all different versions of lipids that we actually consume. And so for our body, lipid is actually considered a good long-term energy source. Lipid actually also is the structural foundation of cell membranes. So later on when we actually look at the cells, we'll see that we see a lot of different lipids within different lipid components within our cell structure and our cell membrane specifically. Lipid is also waterproof, so that means it's not soluble in water, and it can actually function as an insulation. And we actually have lipids being able to function as a cell signaler. So these are like different hormones in our body. It can actually function as a way for our body to communicate, for the cells to communicate with one another, is through these hormones. So an example of that would be testosterone and estrogen. And so lipids can exist in many different forms. The most common one is these fatty acids. So most lipids will contain fatty acid, and this is the lipid monomer. So here is an example of these fatty acids right here. This is a fatty acid. Again, it has a carbon backbone, and it has hydrogens here, right? And it can have different variation of R. So just think of our group as another molecule over here, and there can be many different ones that can be attached to here. And then you have this hydroxyl group and this carbonyl group right here. So when we have multiple fatty acids like this, we can actually combine them together and actually form a phospholipid, right? So here we have our fatty acid, and here we have what's called a glycerol. Head over here because it won't let me draw. A glycerol. And how do we combine these together? Well, you guys should recognize this, right? We're going to do a dehydration synthesis. So we're going to take the hydrogen on this molecule and the hydroxyl on this molecule, combine them together, and we're going to do that again up here and here, right? But we're going to dehydrate, which means that when we combine them together, we're going to release some H2O, right? And then by releasing this H2O, we're able to link these three fatty acids to the glycerol. And down here, what we end up with is 3 molecules of water and this molecule right here that we know as fat. And so lipids can also exist in this fused ring format known as sterol. And sterols do not have fatty acid, but what they have in common with the fatty acid over here is because they're mainly made of carbon and hydrogen, they're also insoluble in water. Okay, so let's kind of take a look at fatty acids. So here are some examples of different fatty acids. This is the primary component of fat and oil, right? So we tend to recognize fat as oil and as butter, right? We also can recognize it as trans fat. So you might have heard that word before, trans fat. This is found a lot in different commercial products. So let's first look at this. So this is canola oil. And so this canola oil, this is a fatty acid. So it has a bunch of, each one of these black guys is a carbon. So this is a way that we, a lot of times, in chemistry and organic chemistry, will recognize different atoms and how we see them linked together. And each one of these white is a hydrogen. So what you have here is actually a carbon bond, and has a double bond. So there's 2 branches right here and here, and so we have two bonds here. This is a double carbon bond, and this double carbon bond you can kind of imagine when you have just one bond, right? You can kind of link and you can kind of move around easily. So I can move around. And so a single bond, there's a lot more movement is able. Once you have a double bond, so here, I can't easily twist it. So this becomes a little bit more rigid because of the double bond. And because it's a little more rigid, it results in what we observe here as this kink right here. So you can see there's a kink. And so it's a lot more rigid. We can't turn around as easily in a double bond. Like if I link two fingers together, I can't just spin around like the way I can with a single finger. And so that's what makes it so that oil has this liquid state because it's not able to line up easily. Whereas in butter, it'll be a little bit easier for us to see in butter. Butter, again, this is carbon, these are hydrogen, this red now is an oxygen. Put here oxygen, right? This is carbon, and let's just kind of label these so we can kind of keep them in mind. And over here is our hydrogen. So you can see here, these are all single bond, right? Single. I mean, there's a double bond right here between this carbon and oxygen, but that's all the way to the edge. It's all the way over here. We always have the carboxyl group is never in the center of the compound. The carboxyl group is always kind of on the edge right here. So we're going to focus on right here. So if we look at this chain of fatty acid right here, they're all single bond, which means they all can move around, and they also don't have a kink. So you can imagine when you have a kink, you are going to take up more space because now we have the space here and here, right? Whereas without that kink, we can lie flat, so we can put in multiple groups of these fatty acids together, right? And that's what saturated fatty acids are. We can line them up multiple together so they can form a solid because they can kind of compact together a little bit easier. So, here's a carboxyl group right here too. So in unsaturated fatty acid, such as oil, we have these double bonds. In saturated fat, we have no double bond. They're all single bond across. And trans fat is a little different because trans fat is also unsaturated fat because of this double bond right here. But double bonds in nature pretty much exist in this way. They are cis, meaning they're on the same side. So this would be a cis double bond. CIS for cis. So this is a cis double bond. Whereas in trans fat, again, this is something that we process, and we actually will take a fat and we'll add double bonds to it. So we'll actually take this saturated and we'll add double bonds to it. But when we add the double bonds, they exist as trans. So they exist as one on one side and one on the other side. Remember, this is forming a kink. And so this kink will actually, because of the way it's forming, these two hydrogen are not kind of taking up space as well, not fighting with each other. So the double bonds existing this way versus here. Here, because of these hydrogen bond, you end up with the atoms trying to give itself space, so it actually forms more of a bend. Whereas here, because they're on the opposite side, we don't form that same bend. And so trans fat can exist in nature. We actually can find it in the guts of many different animals and in food that we make from animals, but it can also be made man-made. So we can actually take a saturated fatty acid and artificially add these extra double bonds. And so why do we want to do this? Well, similar to high fructose corn syrup, trans fat, partially hydrogenated trans fats. So if you look at the back of your food label and you see partially hydrogenated vegetable oil and stuff, all of those are trans fat. And those actually have a longer shelf life. So it can actually sit in the shelf for a lot longer and it's a lot more stable. It doesn't go rancid as easily as butter does. So you have this semi-solid state of the trans fat, so it kind of acts like butter, but it doesn't go rancid as fast. It stays on the shelf for a lot longer. So, I mean, that sounds fine. So why is it that we're told and we're advised to not consume too much trans fat. Well, that's because trans fat can actually lead to different health concerns. So one of them is actually clogging arteries. Your body has a harder time breaking down trans fat compared to saturated fat. And unsaturated fat has a harder time breaking down trans fat, so it stays in your blood system a lot longer, and so it can actually lead to clogging of the arteries, and so that can lead to higher risk of heart attack, higher risk of different type of heart disease, right? Additionally, trans fat has been shown to actually raise our LCL, so our bad cholesterol. So it's been shown that it raises our bad cholesterol, which is again not really a good thing. We don't actually want that to occur. And then lastly, trans fat has been shown to increase inflammation in our blood system. It has some inflammatory markers. So these are all different health concerns that leads to why it's advised not to consume too much trans fat. So if you are if you're trying to avoid trans fat, look at your food label. Look at your food label, and when you're looking at the back of your food label, if you see partially hydrogenated vegetable oil or something along that line, just try to avoid it, or at least try to minimize it in your food consumption. I know these days with the way that we process the food and the cost of food, is so much easier a lot of times to reach for those foods that has the high fructose corn syrup and the partially hydrogenated vegetable oil, because again, they stay in the shelf a lot longer. They typically tend to be more cost effective than buying fresh fruit, vegetable, meat, but there's reasons why they're cheaper and reason why we should avoid them, right? Okay, so let's move on to the next slide, which is going to talk about our other type of fatty acid that we often see, which are phospholipids. So phospholipids, I'm going to erase this real quick. Oops. Phospholipids are found in the cell membrane. We typically find it a lot in cell membrane. So our cell membrane is this outer layer right here. So if you guys remember, when you look at cells and you see that edge, that cell edge is right here. This is our cell membrane right here that we're looking at. And so you see all these different little heads and these different little tails. And so if we zoom in, this is what we're observing. Is this. So this is a phospholipid. So again, it has these fatty acids, these two fatty acids. And remember how I said that we can have different R groups? So here our R group is actually this phosphate group right here. And so this phosphate group, you can see that there's a lot of oxygen right next to it. And so this phosphate group actually is polar. And it's polar because of the oxygen. So if you recall, oxygen has a partial electronegative, partial electropositive, because it is electronegative. So it's electronegative because it really likes electrons. It really likes electrons, kind of pulling at the electrons, which results in it having these partially positive charge associated with it. And so what does that mean? Like, why do we care? Well, that means that because it's polar, it doesn't mind associating with water. So it's actually water soluble. So here, the inside the cells, you can see, and the outside the cell, both sides here, we're actually touching a water-based component. So the head doesn't mind interacting with water because it's actually hydrophilic, so it actually likes water. The tail, however, we can see is carbon and hydrogen backbone, and this is not water soluble. This is nonpolar. So the nonpolar part of these phospholipids, they want to hide from water, so they tend to be inside the, between this lipid bilayer. This is a lipid bilayer because it's made of lipid, and there's two layers. This is layer number 1 up here. This is layer number 2, and so all the tails are kind of hiding in that lipid bilayer because it's trying to avoid water. And so our cell membrane, this function, we'll see this more when we talk about cells. This functions as a way to make it so the stuff that's inside the cells stay inside the cell and doesn't associate with things that are outside the cell. So in that sense, it basically functions as like a barrier between the inside the cell and the outside the cell. Okay, our next lipid that we're interested in looking at is our cholesterol and our hormones, and those exist as steroids, right? Sterols. Sorry, not steroids. Sterols. And so sterols has a function of these 4 fused carbon rings. So you can see each one of these has 4 carbon rings all fused together right here. And remember that each one of these intersections is a carbon, right? So we have 3 different versions right here. We have cholesterol, and so all of them consistently has that 4 the carbohydrate backbone and the 4 rings. So we have testosterone, and then we also have estrogen. So testosterone and estrogen, we typically think of them as different hormones that are in our body, and then we also have this cholesterol. So these are all lipids. So they don't have fatty acid. That's really different than the other 2 that we've seen, right? The other 2 that we saw, the fat and phospholipids, both have fatty acid. So why is it this is still considered a lipid, even though it doesn't have fatty acid? And it's because it still has certain characteristics that it shares with phospholipids and with fat. And that main characteristic is that it's insoluble. So it's water insoluble. So let's just write that down so we can kind of remember. Right? So sterols are water insoluble. And so what does that mean? That means that it doesn't dissolve in water, but it can stay in water, but it does dissolve in organic, specifically non-polar organic solvent. So let's use this opportunity to look at this question. Why is it that you can't dissolve lipids in general, right? For the most part, you can't dissolve lipids in water. So here we have oil that we're trying to add to this water, but you can dissolve it in non-polar organic solvents, right? So you can kind of imagine this is your salad dressing, for example, where you have your oil and your vinegar. It doesn't dissolve in this. However, if you took that same oil and you added to chloroform or benzene or petroleum, it does dissolve. And so what is it? What is the main characteristic that prevents lipids from being dissolved in water? Well, it's because they're nonpolar. They themselves are also nonpolar. Let's kind of write that down. So lipids are nonpolar, right? And why are they nonpolar? Well, they have a carbon hydrogen backbone, right? And they are versus the phosphate group that actually has all the oxygen. So that's the reason why they're not able to dissolve. Is they're nonpolar and they have that carbon hydrogen backbone. Okay, I hope that this gives you some thoughts the next time that you decide to put some butter on your bread. That you think of lipids. Okay, I'll see you in the next section.